Gelos from Università de Mar del Plata. We concern design challenges of oscillating hard float with energy converters. So.
Well, hello, my name is Eugenio. Thank you for the presentation, and I will discuss some of the design challenges that arise for oscillating arm floats wave energy converters. So first of all, I want to give a little bit of context. I am conducting my PhD studies in the Universidad Nacional de Mar del Plata within the Instituto de Investigaciones, Científicas y Tecnológicas en Electrónica. And both institutions are located in Mar del Plata, which, as you can see, is a coastal city, which a lot of activity related to the marine activities. So, moreover, a moderate wave energy resource can be found here in this zone, and overall, the academic presence, the easy access to the sea, and also the surrounding infrastructure and the moderate wave energy resource renders Mar del Plata a favorable location in order to conduct wave energy research and testing different prototypes. So over the years, a wide variety of WECs have been developed, and several methods have been proposed to classify them, mainly according to location, working principles, size, and orientation. In particular, we are working with an oscillating arm float, or OAF, which is very similar to the wave start energy, that has only 1 degree of freedom given by the joint that is placed at the base of the arm. So the first big design challenge that we are discussing is related to the WEC dimensioning. So one of the main design challenges is to adapt the WEC characteristics to a particular wave climate. And this implies to optimize the fundamental design parameters in order to adapt to the desired location. For this purpose, we have proposed a dimensioning method consisting of 3 consecutive steps that I will briefly explain in the following slides. More details can be found in the article itself. So typically, the 1 degree of freedom's OAF-WECs hydrodynamics are described using Cummings equations in the arms joints reference frame, which is the reference frame located at the base of the arm. This equation is a one-dimensional equation in which the hydrodynamic coefficients are all purely numerical. And this is one of the main limitations of this approach for design purposes, because the hydrodynamics coefficient being purely numerical, when changing some or any of those design parameters, then the BEM software have to be run again, and a recalculation of these hydrodynamic coefficients needs to be done. So in order to avoid this limitation and others, what we propose is to start from the float 6 degree of freedom hydrodynamics described in the sea-keeping reference frame using the Cummings equation, which are 6 motion equations in which all the hydrodynamic coefficients are 6 by 6 matrices. Then, by adding the WEC's specific motion constraints and also choosing a convenient reference frame to state the problem, we can reduce this 6 equation of motion to only a one-dimensional semi-parametric equation. In this formulation, the excitation, radiation, restoring, and also the WEC's moment of inertia explicitly depend on the WEC's fundamental design parameters, such as the angular I can see the colors. Well, such as the angular position of equilibrium, the arm length, and the distance to the float's center of mass, the float radius and its draft, and also the arm float total mass and the relations of masses that these bodies have in between them. So, One of the benefits of this approach is that only one NEMO run is required. Also, it allows to study all the different contribution of each of the oscillating modes independently, and also it allows to study the influence that the fundamental design parameters have on the WECs power absorption. And finally, it simplifies the design parameters optimization problem statement that we will see later. Some of the limitations that our current approach is that we only consider an axisymmetric float, and also only one wave direction was taken into account. So, the next of these steps, the next step of the dimensional method that we propose is related to processing the wave resource occurrence matrix and calculating the WECs power matrix. Then by multiplying them point by point, we can obtain the WECs energy production. So some of the limitations that our current approach has is that we only have available regular waves data, so we need to include irregular waves scenario and also to include WECs relevance constraints and realistic contrast strategies. And this I want to emphasize that these two factors are key factors in order to obtain meaningful dimensioning results. So in the third step, we propose a procedure to determine the WECs design power that mainly what its purpose is to avoid the oversizing of the WECs component, and also we design a procedure to tune the WECs resonance frequency based on the semi-parametric model that we derived on the first step, in which the frequency can be tuned by properly adjusting the mass relationship in between the float and the arm, given by the factor f that we see in the equations provided. However, the main limitation of this proposal is that the WECs optimal design parameters are not guaranteed for the given wave climate. All in all, we are currently working on overcome each of these limitations by formulating a design parameters optimization problem, in which the 3 consecutive steps are maintained. However, on each of those steps, key modifications were made in order to improve the overall method. So, for example, in step 1, we consider generic geometries for the float and also all waves direction. That means that the orientation of the WEC is suitable to be optimized also in this new formulation. Also, we normalize the semi-parametric model in order to enhance its versatility. Then, in step 2, we consider irregular waves and also a suitable control, as well as the WECs relevant constraints in order to calculate the WECs power matrix. Finally, in step number 3, instead of defining some parameters in order to align with some design decisions, what we propose is to evaluate an energy cost functional which will modify the design parameters iteratively for the process to continue iteratively until the energy cost functional is reached. Okay, so the second design challenge that we are discussing is related to the power takeoff development. And through the years, many PTOs have been developed, and the most common working principles are based on both hydraulic and pneumatic systems, and also direct linear electrical and mechanical drives. In particular, we are working with a mechanical PTO that includes a mechanical motion rectifier. This is a passive mechanical motion rectifier, which its main function is to transfer the bidirectional motion at its input shaft into a unidirectional motion at its output. Well, some of the benefits that Pedro has mentioned before too is that the more consistent speed at the output shaft results in a more consistent speed at the output shaft, avoiding the low speed, low efficiency regimes of the generator. It reduces the backlash and impact forces and also the fatigue. And also the MMR can broaden the power absorption bandwidth, and the disengaged ratio can be exploited in order to enhance the energy production. However, some of the challenges of including an MMR in the PTO are related to modeling its nonlinear dynamics and also the design of energy maximizing control strategies due to the inherent nonlinearities. So in order to model this system, what we propose is two different approaches: an electrical analogy and deriving the explicit motion equation along with the switching laws and nonlinearities. Well, for the first of these approaches, what we propose is to subdivide the system into three main groups: the fluid structure interaction, the mechanical motion rectifier itself, and the control load. For each of these main groups, we derive the fundamental blocks associated with the physical phenomena, which for each of them we provide a mathematical framework by which an electrical analogy can be derived. Additionally, we derive some basic kinematic constraints which allow us to connect each of these fundamental blocks in between each other, and overall, following this process, we've been able to synthesize the equivalent circuit. So some of the benefits of this is that this process does not rely on an explicit MMR equation, and the complexity of their nonlinearities are avoided. And it's also particularly suitable for modeling the generations stage and also its associated power electronics and control loads. Further improvement that we need to take care is to include the MMR friction losses. So some more details can be found in the RPIC article that was presented a week ago. This is the resulting circuit after applying this procedure. You can see that the MMR is a range of transformers and ideal diodes, and the control load is has a proportional integral derivative action given by the resistor, inductor, and capacitor. So having derived this circuit, we come with a suitable platform to test different control strategies. In particular, we have tested the reactive control, which is a strategy conceived for linear WECs and regular waves excitations. These linear WECs can be represented by the linear circuit that we can see in the image from my right. And the reactive control is based on the impedance matching, which typically in the wave energy literature is unfolded into the optimum amplitude and phase conditions. In particular, the optimum amplitude conditions considers that the only tunable parameter from the control load that is at the right is the resistor. So the optimum is given when this resistance has the value of the WEC's impedance magnitude. So in order to evaluate how the MMR's nonlinearities affect the implementation of this reactive control, what we did is to propose two different scenarios, frequency scenarios. One that is below the WEC's frequency and one is above the WEC's frequency. And we have obtained the steady state mean power absorption for each of these cases as a function of the resistance and reactance of the control load, as we can see in the two figures. So some of the key results that we found is that a negative reactance, meaning that we devise a capacitor at the control load, results in zero mean absorbed power, and this can be explained easily by the electrical analogy because the capacitor always charges with the same polarity, and it behaves as an open circuit in steady state, so resulting in zero mean absorbed power at steady state. Some other interesting factors is that the maximum power for the frequency below the WEC's resonance is near the optimum amplitude and phase condition of the linear WEC. And for the frequency that is above the WEC's resonance, the optimum power, the maximum power, occurs for zero reactance. Also, we can see in these figures that the power absorption is much less sensitive to variations in the resistance and reactance in the MMR WEC in comparison to the non-MMR WEC. Due to the MMR's inherent nonlinearities, a closed form for the PTO optimal control cannot be defined so easy to our best knowledge. So what we did is to a time domain optimization, in which the cost functional to maximize is the steady state mean absorbed power. Here we have the velocities with its nonlinear behavior. So some of the results in that way we obtain the optimal resistance and reactance for the most common ocean wave periods. Some of the results indicates that the optimal resistance is always, which is the solid blue line, is always within the optimum amplitude condition, and the optimal reactance is always near the optimum phase condition. And in particular, is always greater than 0 because devising a capacitor at the control load results in zero power absorbed power, and in particular for those frequencies equal or above the WECs resonance, the optimal reactance is 0. So another interesting thing that we found is that the disengaged ratio, which is the dot line there, the increment of this can be related to the increment of the moment of inertia of the control load. However, this increment of the disengaged ratio does not imply always an increment of the power absorption, which is the solid orange line that we are seeing here. Well, the second approach that we make to derive the motion equation of the MMR-WEC is to derive the explicit motion equations. So for this purpose, what we did is to derive a generalized model of mechanical motion rectifier-based systems in which the dynamics can be fully described by a set of coupling modes under corresponding switching condition, including the so-called disengagement condition. This model facilitates also a simple method to activate all of these introduced coupling modes. Well, this model was experimentally validating using an MMR prototype designed and built in-house, demonstrating the model accuracy in replicating the system's nonlinear response. So this figure, what we see is how the MMR's coupling modes can be controlled by following the switching laws and model that we were previously mentioned. In the first stage, we have a damping load, which is a very simple case in which we can see the typical engaged-disengaged nonlinear dynamics. In particular, the black dots represent the disengagement impedance. And in the second stage, it's a little bit more interesting because the MMR is controlled in such a way that the disengagement condition cannot be reached. Therefore, what we can see is that the MMR always remains disengaged throughout the entire stage. Also, the third stage, by properly adjusting the MMR control parameters, we could disengage arbitrarily the MMR at the beginning of this stage and to maintain this, the MMR disengaged throughout the entire stage. Additionally, in stage 4, what we did is to intentionally lock the MMR, and this state could be very useful for implementing some WECs control strategies such as latching control, for example. Well, and the last one, it implements a Coulomb-like torque, which is nonlinear. So to conclude, I would like to share with you some questions that we ask ourselves, and we think it is interesting to discuss here in this workshop. So the first one is how sensitive are each of the design parameters to the different wave climates? What is the best way to include the economic factors into the design parameters optimization problem? How to adapt the design parameters optimization problem when using an MMR-based PDO, and how the MMR nonlinearities and its associated coupling modes can be exploited in order to maximize the energy production. So thank you very much. I am very grateful to have this opportunity to present this for you. Nothing else. Thanks.
Thank you very much, Eugenio. We have time for one question. John?
Thanks. It's a lovely presentation, and I'm interested that you use an electrical circuit equivalent. And as an electrical engineer myself, I think I would have found it hard to resist the temptation of putting in a full bridge diode rectifier to represent your MMR. I'm not sure it'll help you at the end of the day because it's still going to be a nonlinear circuit element. But you know, the switch-on voltage for the diodes could be equivalent to Coulomb friction in your MMR or something. You know, did you consider that at all, or do you think it would help? Maybe not.
To include the full rectifier bridge?
Yeah.
Yes, we have considered that. This circuit can be more compact, like you say, by replacing all the transformers by this full bridge rectifier. What we have to do is other thing that we've been working is about the MMR losses, and we have to adapt because each of these components has its own losses. So we have to, if you see this model, every component is moving to the left. It moved to the left and to the right of the nonlinearities. So that allows us to make a more compact model and to analyze only the input and the output. So yes, we have considered to.
Thanks.
You're welcome.
Okay, thank you, Eugenio. So